Okay, so if you remember, right, hopefully from yesterday, the longest increasing subsequence was in this example here, we had A was the sequence 3, 2, 8, 4, 7. And the longest increasing subsequence is that I hop from number to number, going from right to left, I guess. I'm getting confused because of the way I'm facing. For you guys, sorry, from left to right. And as I hop along, the numbers have to be increasing, right? And so two solutions of length 3 here are to go 3, 4, 7 or 2, 4, 7. And so we were posing a dynamic program to find the longest increasing subsequence. And our idea was pretty simple. It kind of built on what we've been doing in finding paths in directed acyclic graphs, was that we thought of that sequence as a graph where we connected 2 nodes in the graph. If the index of I is smaller than j, then we draw an edge, and the value of I is smaller than the value of j, then we draw an edge from I to j. And this graph is acyclic because it follows the ordering of the indices. There's all the edges go to higher index, like go from an AI to an AJ where j is greater than I. And then our algorithm just looked like this. We looped through the vertices from 1 to n, where that's the index of, or the AI values from 1 to n. And we do the update that Lj is equal to the max of the incoming Li's, the ones that have an edge coming into j, plus 1, because now I'm doing 1 additional value in my subsequence. And then I return the Lj that has the largest value. That finds the largest subsequence, longest increasing subsequence. And so when we were kind of mapping this to my description of dynamic programming, we had the 3 ingredients. The subproblems were these L values, which is what's the longest increasing subsequence ending at the jth number in the sequence, right? That's Lj. We had an ordering of subproblems, which was, in this case, the topological ordering of the graph, which is just the indices of the, sequence sequence number 1, sequence number 2, and so on, going up to n. And we also needed this notion of smallest subproblems that we could solve directly. And those are going to be all the nodes that have no incoming edges. Or in other words, in the sequence, it's all the values where there's no smaller value to the left, right? So 2 and 3 have no incoming edges. And that was it. So let me just give you an example that kind of draws how, well, we'll do it for that one I just showed you, where we construct the graph and just look at how the updates work, just to spell it out a little bit more. So we have, let's say we have A, again, is the sequence 3, 2, 8, 4, 7. And so I'm just going to create the vertices 3, 2, 8, 4, 7, like this. And then I draw edges between all vertices going from left to right, where it's an increasing, like the number increases. So from 3, I will have edges to 8. To this graph gets quite a few edges in it, to 4 and to 7. From 2, I have edges to the same ones, to 8, to 4, and to 7. From 8, I have no outgoing edges because everything to the right is smaller. And from 4, I have an edge to 7. And now I also have like these are the values at those positions, but like this has index 1, this has index 2, index 3, index 4, and index 5. So when I talk about the subproblem L3, it'll be the longest path ending at 8, right? The third vertex. So then what's our algorithm just runs through. It begins by solving L1. L1 is the longest increasing subsequence ending at 3 at the first vertex. And it's just going to be 1 plus the max of the empty set because it has no incoming edges. So that's 1. L of 2 is 1 plus the max of the incoming edges. But the second vertex also has no incoming edges. L3 is 1 plus. So L3 denotes the third vertex, right, which is the 8. 8 has an incoming edge from 2, like the second vertex, and from the first vertex. So it's going to be 1 plus the max of L1 and L2. Both of those are 1. So we get a solution of 2. L4. The fourth vertex is 4, actually, and it has incoming edges from 2 and from 1. So it's going to be 1 plus the max of L1 and L2. It's also going to be 2. And then L of 5 is 1 plus the max. All the incoming edges from 7, it's got 3 of them. It has 1 from 1, from 2, and from the fourth vertex. L1, L2, L4. And the fourth vertex has the high, like L4 is already 2, so this gives us a 3. And so that's then our solution. And you can see that I could be using prev pointers to keep track of the actual path as well, right? So L1 and L2 have no prev pointers, but then I could write like prev of 3 equals the vertex I found it from. I don't know, we get to choose because both L1 and L2 have a value of 1. So let's say it's 2. And then I would say the prev of 4 is either 1 or 2 as well. And then the prev of 5 is I found it from 4, right? L4 was the one that achieved the max. And so then I could follow those pointers back, right? Like 5 points back to 4, 4 points back to 2, and 2 has like no parent. Because the sequence starts there. Same with 1, I guess. So we didn't write the prev thing into the pseudocode, but it would just be adding an extra line, just like with Dijkstra's and the other ones. Okay. So I'm going to claim that correctness follows directly from our knowledge of paths in directed acyclic graphs, that they all follow the topological order. And so we're exploring every possible path and we're recording the longest one. So I won't go into the correctness in more detail here. In terms of runtime, so one thing that you could think, right? Once I have the graph, it feels like I'm just doing a graph search, right? So it should just be like big O V plus E, because it's linear time in the graph, right? We know that when I'm doing a shortest path or longest path in a directed acyclic graph, it's linear time. The only other thing is I have to construct the graph. And the one thing to note when constructing the graph, let me just go up, is my construction is a little bit unusual in that I'm taking Lj as the max of all the Li, where Ij is in E. So I'm updating the head of the edge by searching over all tails. Do you know what I'm saying? in comparison to breadth first search or depth first search or whatever, I'm always at the tail and I say, what are the outgoing edges? Right here, I need all the list of incoming edges. So I actually need like kind of a different data structure just to store that. Instead of an adjacency matrix storing all the outgoing neighbors, I want all my in neighbors who comes into me. So basically the pieces that I need is I need to construct that like adjacency list of in neighbors, and then I just do a graph search on it. So I'll describe the runtime. We're not really focusing on runtime too much in this example. I'm trying to focus on dynamic programming. So there may actually be a better way to do this, but I'll just write out one way to do this. So construct the graph. And as I said, we want to record incoming neighbors. And the key word here is incoming. So definitely this can be computed in big O n squared time. Right? What all I do is for every pair of vertices, every pair in the list, in the sequence, I just check if there's an edge for that pair. Right? Is I less than j and ai less than aj? It's actually a slightly better way to do this, but like I said, I'm not focusing too much on the runtime. This is certainly an upper bound on the, like for a very naive way of constructing the graph, that'll work, right? N squared. And then computing LJ is a max over all edges incident to J. So in total, it's this, the runtime for that part is going to be like, now that I have a graph, is big O of E. Which, relating it back to the input of the problem, which is the sequence of A, right? That's big O n squared. For sure, there's at most n squared edges. And so the runtime then is big O n squared. Or in terms of the graph, it would be V squared plus E, but that I construct. And then one thing I wanted to mention is this is not the most efficient algorithm for finding the longest increasing subsequence. There's a better algorithm that's based on binary search that achieves an n log n runtime. But the focus right here, that's kind of like, you know, our first algorithm for multiplication wasn't the best either, right? And then we kind of improved it. And so, but the point here is this dynamic programming framework of identifying subproblems, identifying an ordering and a recursive relation, and identifying the smallest subproblems. So let's go on to another example. We'll do 2 more examples today. So the next one is called edit distance. Any questions on the last one before I move on to this one, or we're okay? So in edit distance, the motivation is this, like in spell check, let's say you have a misspelled word and you want to find the closest word under some metric that is in your dictionary, you know, like the closest real word. And so you're kind of doing some distance calculation, like how far is this misspelled word from various real words? One measure of how far apart two words are is called edit distance. And the idea is, how many edits do I have to make to word number 1 until it is word number 2? And the edits that I can make are kind of substitutions or like adding in spaces. I'll show you exactly how we do edits. So let's say I have two words, house and hose. What I think about doing is aligning the words one on top of the other and looking for mismatches. And I want to find, let me show you two ways I could align those words. So alignment number 1, I write house, and below it, I'm going to align hose. So one way would be I put the H under the H, the O under the O, I insert a blank, I put an S under the S and an E under the E. And then the cost of that alignment is I just go column by column, and I incur a cost of 0 if the characters match, and I incur a cost of one if the characters don't match. So when we go through, H matches H, O matches O, U does not match the blank that I inserted, S matches S, and E matches E. So I get a cost of 1x there. Another possible alignment is not as good, but I'm just going to show you another one, is what if I just stack them one on top of the other? I have to make them of equal length, so I insert a blank at the end of hose. And now the first one matches, the second one matches, U and S don't match, S and E don't match, and E and blank don't match. So this one gets a cost of 3. And then the edit distance problem is, given two strings, find their best alignment. Find the minimum cost alignment, which I think in this example, this is the minimum cost alignment. You can't get better than a distance of 1 but for those, because they don't match perfectly. So edit distance between two strings is the cost of the best possible alignment. And cost of an alignment is the number of columns that differ when I line them up one on top of the other. And the idea, as I said, is it's kind of the minimum number of edits I would have to make to one string to turn it into the other string. Okay. So now what we're going to do is solve this with dynamic programming, right? And maybe some of you have seen this problem before. If you haven't, though, actually just try to think right now, what is a subproblem here? It's not easy. Like I don't expect you to immediately come up with the answer, but this is the sort of the train of thought, right? Is we're going to go through those 3 steps. Identify subproblems, identify an ordering of the subproblems, right? So how I could solve one given solutions to kind of smaller ones, and then identify smallest subproblems that I can just know the answer to directly. And a subproblem is always going to kind of look like, you know, in the last example, it was L of J or something like that, right? One hint or tip when you're thinking about this one is subproblems don't always have to just have one index. Like the previous one was L of J, where J represented where I was in the sequence, what position. I don't know if anyone has ideas. I mean, if you've looked at the notes already, you probably saw what the subproblem is, but if you have a guess and want to throw it out there, yeah. Okay, how do I divide the Oh, I see what you're saying. So that just for people who are listening on the recording, the suggestion was, how do I divide it into kind of groups that are, I think, broken by a space, right? That's an interesting idea. I mean, one thing that I'm unsure of in thinking about your suggestion is, what is the index that I'm going to be using? I guess it's because I don't know how many spaces I'm going to need. So it's like, I could think of one index to represent the first, what's the location of the first space or something, and then another one for what's the location of the second space. But I don't really know how many of those I'm going to need, depending on the length of the string. But it's an interesting, yeah, it's a good idea. Right, yeah. So I could, the suggestion is I could like upper bound the number of spaces by the length of the string, essentially, right? And then know that this is the number of spaces I could possibly need. What if I instead, like, just to take a step back a little, what if I don't want to solve the entire problem at the get-go, right? I'm trying to just solve a piece of it. This is usually how we approach these dynamic programming problems, right? If you think of subsequence, maximum increasing subsequence, rather than trying to find the whole one, I tried to find what's the longest subsequence that ends at the jth number in the input sequence. Yeah.
Start with one blank, or like split it into two sets, and then pick the max of that.
I think I see what you're saying. So just take the first blank, and then you have like what remains or something, and you try to optimally solve that. Yeah. I'm looking for something even simpler. Like, I think you guys are actually onto an interesting idea. Yeah. Just do what? Sorry? Okay, yeah. I think you're kind of starting to get towards the right area. So the suggestion is like, do one change at a time in some way. But if I want to do this systematically, kind of, right? Like, yeah. Okay, the longest consecutive matching, so sort of like HO matching with HO kind of thing. This, okay, yeah, there's another suggestion. Yeah. This, like, I mean, everyone's throwing out interesting ideas. And this is the thing that I think makes dynamic programming kind of challenging, is you come up with an idea, it kind of makes sense, and then you try to convert it to like, okay, here's my subproblem. It's defined as E of J, and that equals this thing, like concretely what it is, right? And then here's a recursion. It starts to get really tricky, right? To convert your sort of intuitive idea into a concrete thing. But what you just suggested is really good, because I immediately understand what you're saying. And what the idea was, what if I don't try and match the whole word? What if instead I just say, what's the best matching of HO with HO? Or what's the best matching of H with HO? So in other words, rather than matching the entire first string with the entire second string, what if I find the best alignment of the first J characters or first I characters of the first string with the first J characters of the second string? Yeah.
So could you represent that something like values of the original index, of the original of like the short term later on, and
Yeah. We're not even, I'll even be able to do it without having to like explicitly represent how many blanks I've used. We'll just use that in the cost. So for example, let's suppose I knew how to align, I don't know, the first character of the best alignment of the first character of H with the first two characters of HO. And now I add one more character to either the first string or the second string. And now I want to write the answer to that alignment as a function of the answers to the smaller alignments. So let's try and build this out. This is not a really easy one. And I think this is why in dynamic programming, seeing some examples really is all that can help you get good at it, you know, or like, but here's the idea. So need to have, what are the subproblems here? So the subproblem is going to be, what I'm going to say is edit distance so maybe I'll say just a second. So let's say our input is given x, which is a string of length m, and y, which is a string of length n. Then my subproblem is going to be the edit distance between a chunk of x up to I and a chunk of y up to j. So I is less than or equal to m, j is less than or equal to n. And for some reason in making these slides, I didn't leave space to write that. There should have been a blank there, but there's not. And so I'm going to call this subproblem. Here, sorry, I'm just going to write it here. Call the subproblem EIJ. So that's the best alignment between the first I characters of X and the first J characters of Y. And now, so that was supposed to be step number one. What are the subproblems? Step number two is now I need to have an ordering of the subproblems and a relation linking their solutions. So what I'm going to try is, let's say I add, so let's look at the alignment for, for X from 1 to I and Y from 1 to J, right? Because somehow I want to write that solution as a function of the solutions to the smaller ones. So what can happen? What are the possible alignments of, like, let's just think of what could the last character look like in the alignment between those two words? So the last column. Well, there's only three possibilities, right? In the last column, I could line up xi over top of yj. Or I could line up xi over top of a blank. Or I could align a blank over top of yj. Right, that's it. And then what remains is going to be another subproblem. So the last column will be, number one option is that I put xi over a blank. Option two is that I put a blank over yj. And option three is that I actually align them properly. Or not properly, but I put xi over yj. And in a number one, the subproblem that's left over, after I'm going to get, like, this doesn't match, right? So I'm going to get a cost of 1 plus what's the remaining problem here? It's just going to be the alignment of x. Well, maybe I'll just write it like what's left over on the left is x from 1 to I minus 1. And I have to align that with y from 1 to j. Right, like that, the rest of the word that appears here is going to be x from 1 to I minus 1. And here it's going to be y from 1 to j. And then this is the last column. So, and then the second one, it's going to, what remains after I do that last column is going to be all of x from 1 to j aligned with y from 1 to j minus 1. And in the third case, it's x from 1 to I minus 1 aligned with y from 1 to j minus 1. Plus, I either incur a cost of 1 if these two characters don't match, or I incur a cost of 0 if they do match, right? Because I don't know yet, like those might match or might not. So those are like my 3 possible ways I could do this alignment of the last column. So for number 1, we get 1 plus the cost of alignment of x1 to I minus 1 and y1 to j. And so that's just going to be 1 plus e of I minus 1 j. For number 2, we get 1 plus, now it's going to be the alignment of all of x from 1 to I with y from 1 to j minus 1. And for 3, we get the alignment of the remaining part of the 2 words, plus, and then I either get a 1 or a 0, right? I get plus 1 if xi doesn't match yj, and I get a 0 if xi does match yj. And let me call this thing here diff ij, this whole function here. And so which alignment I should use is the one that's the cheapest of those 3. And so, any questions just on what I'm doing here? Like, is it making sense? I'm trying to write the solution of EIJ in terms of the solutions to EI and then a smaller index than J, or so smaller index comma J, right? Like I's and I primes and J primes that are less than or equal to I's and J's. Because then I could fill those ones in, and then once I filled those ones in, I'll be able to fill in EIJ. Yeah.
If we assume that x is like I is greater than
I think you need both of them. I guess you're trying to say that I only need to kind of do half of the array. I don't immediately see. I think, yeah, I'd have to think about it after. But okay, so let me write then this this right here then is the recursion I'm talking about. Is the edit distance for ij is the min of these three options. The first one being what we called number 1, this one being number 2, and this one here being number 3. And so really my dynamic program is just filling in a big matrix, right? A two-dimensional like table where I is the row, indexes the rows and J indexes the columns. And I can now think of like, how can I fill this table in such that by the time I try to fill in EIJ, I've already filled in these three quantities, EI minus 1 J, IJ minus 1, and I minus 1 J minus 1. Then I can just fill that next one in. So that's this last part. What order do we solve subproblems in? And you can see that we need to solve EI minus 1J, EI J minus 1, and EI minus 1, J minus 1 before we solve EIJ. And so this kind of looks like, if you think of this table, then to solve this ijth entry here, I need these three solutions, right? I need this one, which is this one and this one. Or let's say this is the ith row and the jth column. So I can do it in two ways. I can either loop over I and then J, or I can loop over J and then I, right? I can either go by rows, fill in the entire first row, then fill in the entire second row, then the third row, and then this row, right? By the time I get to here, I will have filled out this row and everything up to this entry. And so I will have had these three values by the time I try and fill out that one. Or I could go by columns. It would work as well. Why don't we take a 5-minute break and then we'll just do the smallest subproblems and then I'll draw an example of this. So the last piece I have to fill in, right? We've identified our subproblems, which are EIJ, the best alignment of X1 through I with Y1 through J. We identified the recursive relation, which is what I wrote above, and the ordering of the subproblems. And now we have to say, what are the base cases or the smallest problems that I can immediately solve to start off my recursion? And these are just going to be, what's the alignment of, let's say, X1 through I with the empty string, right? With like, I have nothing yet in Y and I just have some of X. So there'll be aligning E0. So that means none of X with the first J characters of Y. Or aligning I with the first I characters of X with nothing from Y. And so what would be the cost of this? How many edits do I have to make to an empty string to make it look like a non-empty string of length J? What do people think? 0, 1, J? I'll give you 3 options. J? Yeah. I just have to like, I mean, if you think about it, I just type out the word, right? Like to make X, which is currently empty, look like a string of length J, I just have to type those J characters or insert J blanks basically, right, into X, which then gives me an edit distance of J. So this is just going to be J. And this is going to be I, right? Edit distance between an empty string and one of length I or J, depending which subproblem we're talking about. And that's it. Now I've got my full algorithm, which just has the 3 pieces. These lines are just doing the initialization, which is the smallest subproblems. And then this part is fill in the table. And then here I return EMN. That's the alignment of the entire string of X with the entire string Y, right? So that's the alignment cost of the full strings. Yeah. What? Well, because if we go back up to this picture, sorry, this one here, I'm trying to fill in this table, right? So it's like, I want to have the answers on the edge of the table so that now, or like actually it might be back here, so that now I can fill in this using those 3 solutions. So I'm trying to find like the border of the table. Well, yeah, so this is like the zeroth row, I guess, and then the 0th column of that table. And the numbers in there are just going to be like, 0, 1, 2, 3, 4, 5, 6, 7, up to the end. And then I can fill in everything from the table from then on. So looking at this, what's the runtime going to be? Should be really easy to characterize. In the inner loop here, this is what? It's just a min of 3 numbers. So it's a constant order 1 operation. And then, so the bottleneck is just doing this nested for loop, right? Just going to be then big O M times N. Right, the initialization loops are just M plus N. So they're not the bottleneck. And one thing that is interesting to think about with these problems is that actually an equivalent way to think of it is always that I'm solving some shortest or longest path problem on a directed acyclic graph. That's like what dynamic programming is at its heart. And so let me show you how this is actually just doing that. And I think one person came up during the break to kind of ask me a question where it seemed like they were visualizing it in that way, actually, maybe without fully realizing it. But every dynamic programming algorithm has an underlying DAG, directed acyclic graph, that links the subproblems. You can think about it, right? It has to be acyclic, because if your subproblems were linked in a cycle, you would have no way to solve it, right? If to solve like EIJ, I needed EI minus 1, J minus 1, and to solve EI minus 1, J minus 1, I needed EIJ. I can never make progress, right? So this construction looks like this. So let ij be the vertices. So the vertices are like my pair of indices. It looks kind of weird, right? Because normally that's our edge notation, but that's a vertex. And then I connect two vertices as follows. So I add the edges from I minus 1j to ij. I add an edge from I j minus 1. It's just my linking of the subproblems to ij. And I add an edge from I minus 1 j minus 1 to ij. And this edge has a length 1. This edge has a length 1. Right? Because we had a cost of 1 to go from that subproblem, I minus 1j to ij. And then the other one has a length 0 if xi equals y, oops, sorry, yj. And 1 if xi is not equal to yj. And now I can draw out this graph and actually what I'm trying to do then is compute the shortest path from the vertex 0, 0 to the vertex mn. Every time I traverse an edge of length 1, I'm basically making an alignment cost of 1, either by aligning a blank with a character or aligning misaligned characters through this kind of diff thing, right? Like I align these two and they don't match. So let me just draw an example. It's like annoying to draw, but that's okay. So I'm going to align house and hose like we talked about. On this side, I'm going to put HOUSE, and along the top, HOSE. So the indices here are like 0, 1, 2, 3, 4. 0, 1, 2, 3, 4, 5. And then I have to put in all the internal vertices. So I'm saying this is going to take me a second to draw, but and now I have to draw all the edges. And so the edges are connecting in those three, like the edges I draw, it's always this edge, and then this edge, where this edge has a length of 0. The diagonal edge has either a length of 0 or 1, depending on if the characters at its head match one another. So how about I draw all the edges of length 1 in red? All the vertical and horizontal edges have length 1. It's a little bit painful to draw this, but okay. We're a third of the way there. You get the idea, but I kind of want to draw the whole thing just because I think it illustrates the shortest path better once we actually have the full graph. Okay, 2/3 of the way there. And now we draw the diagonal edges, right? And the only, how about I just draw the diagonal edges that are free, that cost 0, in green. So they're going to be the ones where the head of the edge matches, right? So H to H, O to O, S to S, and E to E. And then all the other diagonal edges cost 1. Okay. And I want to find the shortest path that starts here and ends here. And so I think like the solution's pretty, now that you have this, the solution's pretty clear, right? You use as many green edges as you can, right? So we go here, oh, make it a narrower line. That's my shortest path. Fortunately, I kind of got rid of all my green, but you get the idea. And so that's the one place I inserted a blank, which is exactly what I did up above, right? We put a blank between O and S so that it aligned with the U. The blank aligns with U. Okay. Maybe I'll just leave that for one more second. Well, I see some people writing. Don't want to like scroll away immediately. Any questions? Just final questions before I go to the next one, which will be knapsack. So yeah, I update. Sorry, it is now. I posted. After I realized how far we went yesterday, I updated the slides. I did post it in a response on Piazza, but I probably should have given it more prominence. There's just 3 more slides, which we may not even get through actually. But. So, like I said, really to figure out how to do dynamic programming, you just have to go through some examples and see patterns on how these kinds of subproblems are identified and stuff like that. So let's go through another one, which is called knapsack. It's a very classic problem in that you have n items. Each item has a weight and a value, and you have a backpack, and it can carry at most capital W in weight. And you want to maximize the value that you stuff in it. So the question is, what is the most valuable combination of items that you can fit into your knapsack, given that your knapsack can carry a total weight of at most W, capital W. And so there's 2 versions of this problem. One's called knapsack with repetition, and then the next one, which we'll talk about, is knapsack without repetition. With repetition, I think of it kind of like the shoplifting problem, that you're going into a clothing store, there's big stacks of every item, so you can take many of them if you like. And so basically there's an unlimited supply of each item, but you just have a backpack. And so now your solution could be to just take all of one big stack of things. But if that doesn't nicely add up to your capital W, you might have a little bit of space left, right, in which you can shove something else. So the fact that you have a capacity W is what kind of makes the problem challenging, because you want to utilize your knapsack as best as possible while maximizing your loot. So let me give you just an example. Let's say we have a weight limit of 10, and there's 4 possible items with weights of 4, 3, 2, 2, and values of, say, $100, $30, $40, and $10. So what should you do to maximize your profit here? First of all, like one thing I think comes to people's mind, which is actually completely the right idea, but not the dynamic programming idea, is to calculate value per weight, right? Like dollars per pound. And basically pick the ones that have the most bang for your buck kind of deal, right? So the top one gets you $25 a pound. The second one only gets you $10 a pound. The third one's $20 a pound. And the last one is only $5 a pound, right? Now, the only thing is that you only have 10 pounds to take in total. So the best solution I can think of is that I take 2 of these. That gets me $200 and takes up 8 pounds. So I have 2 remaining. And then I take that one's much better than this one for my remaining 2 pounds. And so I get $40 more. So I get $240 by taking 2 of item 1 and 1 of item 3. I think that's actually the optimal solution in this case. So same question now, and this is the hardest part of dynamic programming, is what is the subproblem? Now, my hint on finding subproblems is in general, make it smaller in some way. Like don't try it. You don't have to be too creative in what you're doing. Just like somehow think, how do I make the problem smaller? Yeah. So say that again. Start with the lower weights. Yeah. So I think that's maybe I could organize the items by weight or something like that, right? And then just consider the subproblem where I have my full size knapsack, but I only have item 1 to consider. And then I could grow my problem to say, consider items 1 and 2. Now consider items 1, 2, and 3. Is that kind of? So if I understand correctly, maybe you're actually talking about limiting the W here. Yeah. I like that even better, I think. Then the other way you're talking about will actually kind of work as well. But this one, so what if I think my knapsack, instead of having a capacity of W, it has a capacity of W bar that's smaller than capital W. Right. And now if I gave you, if I knew how to optimally pack my knapsack with capacity W bar, maybe I could figure out how to do W bar plus 1. That it kind of makes sense because I know how to solve, like the idea of a smallest subproblem is going to make sense. Like how much can I fit into a knapsack that can hold nothing? Nothing, right? Like, so the smallest subproblem has a clear solution, which is 0, if my capacity is 0. And I know how to extract the actual answer from it, which would be just use the full capacity of capital W. So I like this idea. So I could define K of some W bar. That's going to be my subproblem, which is max value with capacity W bar, where W bar is less than or equal to my capital W. And then my end solution like my goal is to compute K of capital W. Right. Often in an exam or like on the final exam, it'll break a dynamic programming problem down into a few steps and I'll say, define the subproblem, right? Like what is the subproblem? Might even give a hint, you know, to get you started, right? And so you would write something like this. And then it would say, how do you find like the answer from your subproblems? And then that would be like this, right? Just K of capital W. Here it's super obvious. I mean, how you find your solution. Sometimes it's not so obvious how you find the end answer from the subproblems, or you have to, like for example, in longest increasing subsequence, it was the max over J of Lj, right? That was how you found the end answer. It wasn't just like L of N. So now how do we relate this to smaller subproblems? So the argument here is, it takes a minute to sink in or to see if you agree with it, but what I'm going to say is, suppose optimal solution to K W bar includes item I. Then removing I from the solution must be an optimal solution. Oops. To K of W bar minus the weight Wi. Does everyone agree with that? My argument would be by way of contradiction, right? Suppose, so K of W bar, that optimal solution includes item I, but suppose that this wasn't optimal anymore. Or suppose that removing that item I wasn't optimal. That means that there's a better way to pack the remaining portion of the backpack. So I could replace what's in my supposed optimal solution with this even better solution, then add the item I back on top. It would still meet my capacity limit and would get an even higher value. It's like this optimal substructure kind of idea, right? That if I had an optimal solution and I remove one item from it, what's left must still be optimal for the size that's left, the weight that's left. Now, the problem is, of course, I don't know whether or not any given item I is in the optimal solution to K of W bar. But, so maybe actually, so first, before I say that, so therefore we have that if item I is in the solution, then K of W bar has to equal K of W bar minus Wi, right? We said plus the value of adding that item I back into it. That's just restating the same thing that I just said. And so now, since I don't know which item I is actually in it, this must hold. So I'll just write it as I say it. So we don't know if any particular item I is in the solution for K of W bar, but one of them must be. So we can write K of W bar is equal to the max over all the I such that the weight of the item can fit in the backpack. Weight of I is less than or equal to W bar of the expression above, K of W bar minus WI plus VI. Oops, curly brace. So if I is in the solution, this holds, right? If I is not in the solution, then like what's here is greater than or equal to what's on the other side. Because the solution here is this one uses I and the optimal doesn't use I. So like if I is not in it, then I get a greater than or equal to. And so then combining that means that this has to equal the max of all the options. Right, it'll achieve the max for any I that's actually in the solution. And for all the other ones, the value you get on the right-hand side will be smaller than the max value. Smallest subproblems, I think I already said it, right? It's just going to be K of the empty set equals 0, or K of weight 0 equals 0. Backpack with capacity 0 can fit a value of 0. That's assuming that all the items have positive weight, which is if they don't all have positive weight, then the problem isn't interesting, right? Like then you can fill your backpack with infinite value with 0 weight. And then finally, if we just assume that all the WIs are integers, we get the following algorithm, which is I solve my smallest subproblem, and then I just loop through the W's from 1 up to the max value, and I just fill it in. So K of 1 is going to be the max of all the weights over all the weights that are less than or equal to 1 of that same expression. You know, the best way I could fill a backpack with that smaller size plus the value of that item. And then at the end, I return my solution, which is with the capital W, the full capacity. So what's the runtime of this? In the inner loop now, I have to take this max over all the weights, all the items with a weight less than W, right? So that's no longer necessarily a constant time operation. In the worst case, it could be over all the items. So inside, that's definitely a big O of N operation, and then the for loops over capital W, right? So it's just going to be big O and W. Now, interesting question that I'll leave, this will be our last point for today, is this a polynomial time algorithm? I see some yeses. Do I see any no's? anyone think it's not? Yeah. Yeah. So when we talk about polynomial time, we're talking about like polynomial time in the size of the input. So the number of bits I would need to represent W is like log W bits. But this algorithm is scaling not with the number of bits in W, it's scaling with the value of W. So for example, if I make capital W 1 billion, that's still a small input. It takes log of a billion bits to represent, but now my for loop's gonna run a billion times. Or if I make capital W 10 to the 20, right? Like the algorithm will never terminate essentially, even though I can input 10 to the 20 in a small number of bits, right? So it's what is often called a pseudo polynomial algorithm, because it's scaling in the value of some of the input parameters rather than scaling in the number of bits needed to represent them. So we are out of time. Maybe we'll finish there. We could talk a little bit more about that on Tuesday. And then we'll go into Knapsack without repetition.